Thank you. So what I want to talk about today is the ways we have to characterize electrochemical systems at high spatial resolution. And we have the ability to do atomic resolution work where you can see each of the atoms of each chemical species and you can determine composition and bonding at atomic resolution. We also have in situ methods where we can run things in liquid and watch what happens when you apply voltages. And it's very difficult to get both of these together for some fairly fundamental reasons I'm going to talk about, as well as, you know, how much of that we can get around. And then more recently, there's been a lot of work of applying techniques developed for biological electron microscopy for electrochemical systems. And this is, in fact, a lithium dendrite in a battery material at a liquid-solid interface that's all been snap frozen. The work in my group has been funded in terms of personnel by the Department of Energy through 2 Energy Frontier Research Centers, our current one and our earlier one, as well as EERE. And a lot of our equipment and facilities have been supported by the National Science Foundation through our Materials Innovation Platform, which is a national user facility, and our MRSAC, the Cornell Center for Materials Research. So the way people sort of do modern materials electron microscopy is take an electron beam, focus it down to a spot smaller than an atom, scan it around. Electrons that scatter to high angles, this is Rutherford scattering, you scan that around and that's going to form an image. And so, you know, here is my nanoparticle. And the usual trouble with nanoparticles is they're never straight down the zone axis. They're randomly oriented. This is a fuel cell catalyst particle. So you get a couple of lattice fringes arranged like that because it's randomly oriented. You cut a hole in your detector. The electrons that go through the middle let you do chemical analysis. This would be like having a synchrotron, except it has 1 angstrom resolution. And the core level spectroscopy lets you identify cobalt, it lets you identify platinum, put it together, and you can see there's a shell around this material. The screen is a little bit saturated. There should actually be atoms showing up there, but the colors have saturated out. We also get bonding information from an experiment like this, so we know actually the oxidation state of every atom column. And this is technique we sort of developed about over a decade ago, and now it's sort of coming into wide use. And we've used this kind of method. You know, here is a platinum cobalt catalyst particle for a PEM fuel cell. It has an ordered platinum cobalt core, and it has a platinum shell. And the beauty of being able to see things at atomic resolution is you actually can see misfit dislocations in the shell that have relaxed the strain. So the activity is not as high as you would expect when these particles get big, but it's actually pretty good when they're small. You can also see from the chemical map the planes of cobalt and platinum atoms, and then just over here as a reminder of how this material, when it's got a chemically ordered core, has a huge jump in activity over ones that are chemically disordered, and that's basically a strain effect because those two things have slightly different lattice constants, even though the shell is always pure platinum. So we've got very good tools for understanding catalyst nanoparticles at the atomic scale. And the thing you might wonder about is, well, okay, why am I not doing this in situ? And this plot over here explains why. And it's an interesting plot because it's basically, this is the plot that made Richard Henderson give up doing X-ray work and switch to electrons. And just reminding you, he was one of the 3 folks who got the Nobel Prize in Chemistry 2 years ago for his work on cryo-EM. And what this tells you is there's a big difference between imaging and diffraction. And for imaging, you've got to look at the same thing with more than 1 electron or more than 1 X-ray. And what that means is when I'm doing imaging, it's not the cross-section that matters. It's how many damaging events do I get per useful imaging event, right? So if my particle comes in and I have an elastic scattering mechanism that forms my image, thanks, then that'll give me 1 count in the right channel either diffraction or position of the particle I'm trying to image, and then the inelastic scattering is going to cause radiation damage. It's going to break everything up. And when you look at the question of imaging, you want your elastic curve to be as close as possible to your inelastic curve. And for electrons, that's actually pretty good for most beam energies. And for X-rays, if you pick the right energy, that's the best you're going to do, but you have enormous photoelectron cross-sections. And so even in the best case for X-rays, you're going to be 10 to 100 times more damaging than electrons. And it turns out by this analysis about the worst thing you could use was neutrons. Now, this is counterintuitive because everyone knows electrons, interact strongly and X-rays interact weakly, but they interact weakly in both the elastic and the inelastic channels. And as a result, there are in fact molecules we can image at atomic resolution. Polythiophene is one, for instance. But you've got very little prospect of doing that with X-rays. And the X-ray people, as they go to higher and higher spatial resolution, are suddenly discovering they're blowing things up in much worse ways than you would get with electrons. Obviously, if I'm imaging a giant crystal and I get to dose different atoms each time, then these are options. But if I'm trying to look at the same atom more than once, this is the thing you have to think about. And this gives a big advantage to electrons. So that's, in some sense, that's good news. It's still bad news because the inelastic cross-section is bigger than the elastic. So in some ways, it's a little like democracy. It's a terrible method, but it's better than all the alternatives. So you actually, when we get ahead and say, okay, I want to image something, from looking at noisy TV sets, there's actually a statistical limit to how many scattering events I need in order to see something, right? From imaging, TVs with degrading signals, you need at least 20 photons or 20 particles to see something with a signal to, 25 to see something with a signal ratio of 5 to 1, which is sort of a 20% noise level. So just because I'm seeing quantized particles, it's Poisson statistics. If I have n counts, my noise is square root of n, and that's going to set my ability to see things. And so your resolution, you can actually work out how many particles do I need to see something, and the number of particles I need scales with the resolution. Basically, resolution goes as 1 over the square root of dose, and it goes like 1 over contrast. So if I want to have really high spatial resolution, I need a lot of electrons. If I don't need high spatial resolution, I can get away with very, very low doses. I need a good contrast mechanism, and I need a good collection efficiency. I'm going to come back to that one there, because this is the last one we haven't tweaked on yet. Now, you might look at this here, and it turns out that things like water and lithium fluoride are actually fairly dose robust. You might hope that, I can image things at under a nanometer if I have poor contrast and at about 2 angstrom, which is atomic resolution. If I have good contrast, a lot of organic materials damage much faster than that. So over here, typical sort of polymer, I'm stuck at about 3 nanometer resolution in poor contrast and about a nanometer if I have good contrast. So, and that number I get to squeeze a little bit by playing with the contrast and the collection efficiency. And that one scales linearly, which is a pretty big deal. So that's the operating curve I have to work with. And if I start to look at things that are going to be reactive, I want to be down over here in resolution and not up there because I'm going to do terrible things to the sample. And these are calculatable curves. So, maybe I can get to atomic resolution in water, but not an organic electrolyte. But if I want to look at more than one image, just from a dose point of view, I've got to back off. So what do the biologists do? And they've spent about 40 years working on this problem. And one is you can do crystallography. And that's just the same as X-ray crystallography. And over here, from the crystallography all frozen, you can actually see molecules, ions in a channel through the molecule. It's about 2 to 3 angstrom resolution. The technique that really wins out today is the single particle analysis, and by single particle I mean hundreds of thousands. But what you do is you take an image where each image has got a very low dose per molecule, and then you average over hundreds of thousands of molecules to reconstruct in 3D the object you're looking at. And the resolution is at atomic, and if I just freeze the material and image it directly, given the dose limitation, I'm going to be 2 to 4 nanometer resolution. So this is a useful technique to map over to batteries, for instance. Now, the single particle methods by about 2015 got to the same resolution for looking at large biological molecules as X-rays, and today they are actually down well below much better resolution than you can get with X-rays. And the advantage is you don't have to crystallize things. So this should be very interesting if you're doing molecular electrochemistry or bio-echem. You could actually take your molecule, freeze it at an applied bias, and then do single particle reconstructions at different potentials. This is not going to work well for nanoparticles because nanoparticles have far too different a shape from each other, right? And then obviously this is only useful if I have a big molecule, because if it's a tiny molecule I could probably do NMR. So this brings up sort of an issue that you've got to keep in mind. And it's the difference between imaging every single thing and imaging an ensemble average. And when I do diffraction or when I do single particle EM, I'm looking at the average face of everyone in the room. And certainly it tells you that you're human, but a lot of the more interesting details have been lost. And when I have a very radiation sensitive material, this may be the only thing I can do, and I'll take it. At least I know I'm not looking at some other strange alien species. But the main problem is catalysts, like people, are inhomogeneous. And so we're going to try to push imaging as far as we can go. So the first one to map over very easily is freeze the material and look at it. So, you know, with batteries, I normally have a problem. I have a liquid electrolyte. I have a SEI layer. And then I have my electrode, which is made out of something, in case it was pure lithium, something that's not going to like to be exposed to air. But hey, if you do go from glove box to liquid nitrogen, there's no oxygen around in liquid nitrogen. It all freezes out. And so you can use a focused ion beam system to cut into this solid liquid interface that's been snap frozen quickly enough that nothing crystallized. And you'll see, in fact, this is work by Lena Kourkoutis's group, that there, in fact, in this particular material with 2 different shapes of dendrites that are imaged in 3D by basically slicing through, and as you cut out little slices, you get to see what's there. These are the slices that are showing up. She then took a slice out of the cryofib, cryo-transferred it with biotechniques to a TEM. So there's the lithium electrode, there's parts of a dendrite. She can do chemical analysis in the electron microscope. The funny wispy dendrites turn out to be lithium hydride with little bits of lithium attached, and the bulky ones turn out to be the pure lithium. And then you can get to the SEI layer, and you can do a chemical analysis of all the bonding in the SEI layer with a couple of nanometer spatial resolution. So this is basically just, you know, cut it out, freeze it. And the advantage of freezing is about a 10 times to 100 times more dose you can dump on the sample. And a little bit more of some of the chemical identification. Now, this is that was sort of state of the art for what you could do by biology. Now, the one thing that's been missing is, how do I get better resolution? The last thing I can do is I can collect all the electrons, right? If I'm doing a regular image, the only way I'll form an image is I make sure I only collect part of the electrons, otherwise my signal doesn't change as I move the beam around or I look at my CCD camera. So we designed a detector, this is about a decade of work with Sol Gruner, where we could put an electron beam through the material, record the full scattering distribution on a pixelated detector, and throw absolutely nothing away. In order for this to work, required a dynamic range thousands of times beyond what anyone had ever done, and it had to run very, very quickly. So you record a diffraction pattern from a small beam, The immediate payoff from this thing was, normally this is a twisted bilayer of MOS2 because the atoms are sort of at funny angles. It's very hard to resolve any of them except at the center of the Moiré pattern. But with this detector being able to phase all the information from a diffraction pattern at every position, this is, think of this as many, many gigabytes of data recorded in a few seconds, we were able to produce an image that resolved all the atoms. And this is now the highest resolution image in the world by any method ever. And we got there by recording every electron that went through the material. So that is something that has a huge benefit when you start to think about dose. And I'll talk about that in a bit. But it also has the advantage of, if I have a diffraction pattern at every point in the beam, I can now go ahead and measure strain in the material with this very small probe. So it's a diffraction pattern in very tiny spots. And this is work done by my former student, Elliot Paget. And now we are able to map out the strain profile in this core shell particle, and we're able to measure the strain in the shell, including where the strain is relaxed, and do so with sub-nanometer resolution and sub-picometer precision, and it takes about a minute to record this image. So we don't just record one of these, we record ensembles. Basically one every minute or so, and very quickly you have huge data sets. And the beauty of this technique is the dose is 1,000 times less than trying to do spectroscopy or trying to do atomic resolution imaging. So this compromise of, I'm taking an ensemble average because it's diffraction, but I'm taking it from a very small volume, is a nice compromise between trying to resolve every atom in great detail or just blurring over nanoparticles, right? So I can do diffraction in a volume less than a nanoparticle. And this is a nice dose compromise. So where are we at to about now? Certainly the new detector using a method called tychography has improved our resolution, that now you can pick up defects very nicely. This is a monolayer of MOS2, one atom thick except for two sulfurs, and over here I'm missing a single sulfur atom, and it jumps out beautifully. So we can see individual defects if you're trying to think about catalysis. We're obviously able to image things in 3D. These are platinum catalysts inside and outside a high surface area carbon material. And by spectroscopy, if you look at catalysts before you cycle them in a fuel cell and at the end of life, you can see from the chemical analysis over here, I've got, in this system, it's a Vulcan support. I have a huge amount of coalescence of particles as they move around on the surface. If I'm in a high surface area carbon and particles are on the inside, they can't move around and coalesce, but you still see Ostwald ripening and leaching out of the cobalt. So this is sort of a system where microscopy is very nice, because all of these details would be lost because it's a very inhomogeneous aging process if I had attempted to do diffraction. So now the question is, okay, can I do... so before I get there, the detector where I collect all of the electrons has a much better performance curve than the more traditional electron microscopy methods. In fact, if you sort of read off the curve, I'm either going to be able to do the same resolution with 10 times less dose, or I can do, for the same dose, a pretty big improvement in resolution. And in fact, you can get to super resolution at very high doses. But normally, for like EChem systems, we're going to be working over there. So what happens if I attempt to do liquid cell work, right? And the highest resolution is I would make a liquid cell by enclosing a small amount of liquid in graphene, and then I would zoom up to atomic resolution, and yay, I see atoms. The only problem is this is the world's most reducing environment. So what you're actually studying in this liquid cell is, in fact, reduction of a solution of platinum, and you're growing platinum nanoparticles on the walls of your graphene. So that's great, but that's probably not what you wanted to do. That probably wasn't the electrochemistry you had in mind. So a little over a decade ago, we started to build a EChem cell with Tito Abruña, where the idea is there were biological liquid cells. You could take two nitride membranes. We basically designed a system with a carbon working electrode so you could image through it. People had attempted EChem cells before, but you couldn't. They used gold electrodes, so you couldn't image through it. And so this was a system. It's a 3-electrode system in a liquid. I'm not going for atomic resolution, so I can get some slightly stronger windows. nice potentiostat. So here's a CV curve for platinum, from the literature. Here we are in the liquid cell in liquid, beam on and beam off. So we're doing a fairly good job of reproducing the CV curve of a polycrystalline platinum. We, here we've put platinum nanoparticles on a carbon electrode, and you can see the nice capacitance curve for the carbon electrode, and then the nanoparticles are not as well faceted as a polycrystalline material, but hey, I'm doing ECAM in a liquid, and it's pretty robust. So this was important. This was sort of the first time anyone's sort of been able to reproduce something that, a real electrochemist wouldn't be laughing at. And so there's a lot of fun stuff you learn when you start to do this. Here's a very boring experiment. I'm just cycling my carbon support. And what you see in the image is, notice how it's expanding and contracting. It's stretching and shrinking. Those are sort of things you don't think about until you see them. But if you're a materials person, you do start to worry about cycling fatigue and things like that. So there's a lot of unexpected insight you get just from being able to see stuff. I think I'm going to need someone in the back to push play on this video. This is cycling some nanoparticles on a carbon support. Oh no, okay, I think we have a little error, which is what happens when you port from a Mac to a PC. What we're missing is a lovely video of these two particles coalescing. They actually move together over electrochemical cycles. Once they touch each other, they start to reshape and form a single round particle. So we're able to study coalescence in situ. We're also able to get chemical information in situ. One of the tricks is, in very thick liquids, it's hard to do core level spectroscopy because of multiple scattering. But most of my electrolytes have large band gaps. Most of my battery materials have interesting electronic transitions that lie inside that band gap. And so if I look inside the optical gap of the material, so there, down there, hiding there is the optical gap of water. If you take a look what happens, lithium iron phosphate to iron phosphate, when I remove the lithium, I've emptied out the d orbitals, and there's a very nice peak from the d orbitals sitting at about 5-6 electron volts. So vacuum ultraviolet spectroscopy is really, really, really easy to do with electrons. You can also do vibrational spectroscopy if you have a monochromator, but in this case, the peaks I care about are at a few electron volts. They're easy to image directly. I'm going to sit on this peak over there, and now when we electrochemically cycle the material, the things that are going to show up bright are basically when I'm pulling lithium out of the system. And so there we go. You saw a little nice core shell thing flash up over there. The other one to watch for in my next cycle is the solution's going to become dark. See how it turns dark and then it goes back bright again. What's happening is at 5 eV there's a lithium sulfur LiSO4 minus transition, and so the reason why the solution is bright is I'm actually mapping the lithium concentration in this LiSO4 minus transition, and then over there I'm depleting the solution because there's a lot of stuff around there blocking it, and as the lithium gets pulled into the particle, it gets pulled out of solution and it goes dark. So we have an ability to sort of see the chemistry and the composition and the bonding state in the particle and in the material. If you track the cycle, here's a nice particle building up a core shell, and then eventually, in fact, what's happening is, wait, where'd it go? It, in fact, cracked and broke off the material because the lattice constant is so different. And by end of the cycling, you've actually fractured and pummeled these particles. This is basically, one of the other reasons why you need carbon around lithium iron phosphate. Otherwise, to keep it all together after it's cracked and cycled. From my experience with MBE growth, 3% lattice mismatch is huge and usually leads to fracture. And that's supposed to be a low strain material. So last thing I want to touch on over here is length and time scales. This is sort of Esther was sort of touched this is important, but I thought it'd be important to actually put some quantitative numbers on this. So there are two times the length scales we care about. They're transition states, and for EChem, your natural unit of time is picoseconds, and I want to study things for picoseconds and longer, just thinking about the time it takes to reorient molecules in solution and get the water to properly polarize. and the length scales here are angstroms. Today, if you want to do this kind of experiment, it needs to be light activated, because anything that's electrically activated, the sample has too much capacitance. I can do diffraction from crystals, but I can't do imaging. Essentially, pump probe experiments, it's hard to come back to the same thing again in a pump probe. The main problem we have over here is the free electron lasers were designed by physicists to work in the femtoseconds, and that's the wrong time scale. It's hard to stretch out into the picoseconds with the stability you need, and that's sort of a lesson of not letting the physicists design everything. They miss important physics. Electron microscopes are well designed for this, and energy recovery linacs are well designed for this energy scale. So now, we've got a chance to think about this again for the next light source. Ultra-fast electron diffraction is very well suited to this problem. Imaging is much, much harder. There are brightness issues there. The second thing that length scale we care about is diffusion of ions. And you can kind of plug in diffusion coefficients for things and ask, well, how far does it take to diffuse? And for liquids, I might care about nanoseconds. For solids, I might care about seconds. But the length scales scale as well. And this is where we have opportunities for TM and synchrotron. Here is basically, let's pick a diffusion coefficient for a solid. And now when I look at the diffusion time relationship, there are length scales where I'm bigger than about 30 nanometers. There I might as well use X-rays. If it's below 30 nanometers in resolution that I need, then obviously I'll use electrons. The thing you now care about is, can I resolve the time scale? About 2015, that was about our detector speed. Once we built our pixelated detectors and other people came along as well, now we'd pushed into, below a nanometer in diffusion length details that we could pick up. Right now, our new detector we're testing gets us down basically into 10 to the minus 4 of a second. And the things we would like to design, if people would fund us, would get us all the way down to a microsecond per frame of the detector. And that will get you to atomic resolution details. The next thing about bridging the length scales is this problem is already being actively worked on in other fields. In fact, the connectome is a multi-length scale problem. Over here, you want to map a square millimeter of brain tissue at about 30 nanometers resolution. You're looking at about 10 to the 14 synapses. And people are doing this today. The leading methods today are electron microscopy. You can actually map about a square millimeter at, 4 by 4 by 40 nanometer resolution in about 90 days. That's a little slow for us. But if we go to a 1 megahertz frame rate detector, none of these exist yet, although we know how to design it, we should be able to do the same problem at 30 nanometer resolution on an X-ray beamline in less than a day, actually probably about 7 hours. So you probably don't need this big a volume, and so when I've scaled down to, okay, I just need a couple of microns to look at, these things start to become real-time imaging over multiple length scales. 30 frames a second, a couple of microns, and resolution that you could push down to just a few nanometers. So very well matched. Obviously, it means, in this case, huge data sets, but that's why we have big computers. The last one I wanted to touch on was people said, hey, can we see the electrochemical double layer? In fact, when you plug the numbers in, you should be able to see it in liquid cell TEM. If you choose the right ions in solution, because the density of ions would be detectable. The electric field gradients are actually measurable as deflections of the electron beam. It's called differential phase contrast. We do it in solids. We do it for magnetic fields. It should be doable in liquids. And in fact, it might also be possible by X-ray diffraction. This is no longer an imaging. This is an ensemble average. But when you look at X-ray diffraction, this is sort of a, from the diffraction data, you can either try to invert directly or calculate by DFT. This is strontium titanate. There's the density in fluctuations in the water. And then when you've trained the material and now it has some defects in it, the theory doesn't match as well, but when you do a refinement, you can get it to match. And now you see some funny things in the liquid, which tells you I have a superposition of things going on. The main focus of the paper was actually showing the strontium layer was missing. So for their purposes, it was fine. They couldn't quite get all the details there as much as I would like, but with a better dynamic range on the detector that wouldn't clip out that stuff, you can probably resolve some of those ambiguities. Although it's still, again, it's average structure. So very quickly, outlook of things. Electrochemistry in the TM is limited by radiation damage to 1 to 10 nanometers. Cryo-EM extends our dose that we can apply by 10 to 100, which improves the resolution. Single particle EM gets you to atomic resolution by averaging. Great for molecular structures, bad for nanoparticles. Our new high-performance detectors give us much more dose-efficient imaging and again let us push the resolution. They also are fast enough to give us multi-scale. And of course, once I get to multi-scale, I have huge data sets. We generate gigabytes a second. We generate terabytes an hour. And, computers' storage is growing. It's not a big deal. You just need to become more computer literate. We're having a lot of fun working with Google, for instance, on these big data sets. So again, acknowledging DOE for a lot of the support of the ECAM, NSF for the facilities. I should also thank DOE for letting me learn about electrochemistry, because before then I was largely a physicist. And then I have to thank my collaborators, obviously, Tito Brugna and his group for, teaching, being able to partner with great electrochemists, Sol Gruner and his detectors, and that's been a long-going collaboration as well. And then the electron microscopists at Cornell, there's a lot of us. Half of the group is mine, the other half is Lena Koukoudas, and she's the one who did the lovely cryo-EM. I stay away from cryo. And then Tomas Arias for a lot of the joint density functional theory. And I do want to highlight my recently graduated students, Megan and Elliot, who did a lot of work, Megan on the liquid cell, Elliot on the strain mapping. So with that, I'll stop and take questions.
One always worries about what confinement effects might be doing, what would be otherwise a more globally ensemble averaged isotropic event. So with the flexing of the carbon upon cycling, how much of that do you think it was just responding to pressure waves in that thin layer?
There's a steady state flow, but I don't think it would be, it's not fast compared to the electrochemical cycling rate. The liquid structure is, we're a couple of 100 nanometers of liquid, and the particle is, much smaller than that. Yeah. And so, I've got,
Some of the carbon can really agglomerate to a length scale where it might even be spanning the window.
It's attached to the electrode on the top. It's not attached to the bottom. So it's, it's bound to, an electrode, which is kind of what you'd expect it would be doing normally. And then it's free to move in the other directions. And there's definitely, a lot of space down below there, a lot of flow down below there. The nice thing is I can do a little bit of depth section imaging to get a sense of the depth profile, and there's enough space that it's not constrained. We can work to about a micron thick of liquid. I don't like going there, normally prefer about 500 nanometers. Yeah. The bigger problems you worry about are, if I get in too confined a channel, I'm going to have a lot of boundary layer effects, and then I'm going to get much less flow than I would like. That, I think, is the big one I worry about, because I do need flow to keep removing reactants. If I don't do that, it all builds up locally and I get in a lot of trouble.
I would still feel like there's a convolution coming in just from the physical, the mechanical aspects one should keep in the back of the mind.
Maybe we should talk about that later, but I really think I'm at a length scale beyond that.
So So you showed the example of the molysulfide where you said that you were able to identify these sulfur monovacancies.
Right.
So we're seeing in some materials what is really important are sulfur cluster vacancies, and it depends whether they are in trans or in cis with respect to the metal. So would you be able to detect also this cluster vacancy or cluster defects, let's say, and exactly in which arrangement they are with respect to the transition metal?
Yeah, that should be very straightforward. The only caveat is if they're very unstable, right, then you could damage them with the electron beam. So that would be the main one to watch out for. Usually what you do is if you start to see your data set evolving on you, that's a warning that I'm damaging things. That usually it's, you don't take just one image, you've got a set you average, and each one's a little bit noisy, so you can see an evolution through the set if there's going to be radiation damage. But certainly clustering of, a lot of times when people try to dope these materials, the dopants cluster. And those are very easy to see, and you get beautiful patterns, lines and chains. We did this 20 years ago in silicon, and you implant dopants in silicon, and you very quickly see them starting to cluster. One of the main lessons you get from electron microscopy is point defects very quickly cluster into things that are not points, and a lot of semiconductor literature knows all about this, but it's only as we're just starting to image these systems then you learn how important clustering is over treating everything as isolated defects.
Franz Geiger from Northwestern University. So we do a lot of liquid cell EM work, just like you. We're really nice. I love the examples you gave. What are the prospects of getting the approach to a more user-friendly environment, right? Number one, I need $1 million+ microscope. Number two, these optical liquid cells for EChem, for observation of soft matter, etc., under flow conditions are wonderful, but they have maybe a 10% or 5% success rate in terms of assembling them, putting your sample there. That's taking a lot of time out of the researcher to get you to data that really counts.
Yeah, so
where do you think that's going to go?
Yeah, so having watched a couple of generations of my student work on liquid cells, it has a really steep learning curve, and it takes a long time before the loading is very tricky, and the students who've done it a lot are actually really good at it and have a high success rate. And when you're learning, particularly on your own, it's just failure after failure after failure. And microscope time at a university is expensive, so these are really expensive failures. What that sort of points to is this may well be a good argument for national facilities, that, if you can persuade our DOE colleagues to dedicate an electron microscope to goopy liquids, and then have someone who eventually learns how to load these cells for the goopy liquids, then everyone comes and does the goopy liquid work in the microscope, just like you would do with beamlines. And at that point, the cost is transferred to DOE, and you're not seeing it directly. But I think given the skills and plus the risk of catastrophic failure, we don't like working with organic liquids in our liquid cell anymore, given how expensive it was when it leaked. And one of my colleagues was, how do I get all this, organic liquid out of my $1 million X-ray detector? I just cringed when I heard that. And that argues for central facility where you've got trained personnel that, yeah.
Just a short remark. Straight into answer, as a member of the advisory board, SINT at Albuquerque has 3 microscopes. 2 of them are dedicated for liquid, 1 of them for organic liquids, and it's somewhat undersubscribed in terms of user facility. It's not the most popular place to fly, maybe, but that's a SINT, not the gateway at Los Alamos, but SINT core in Albuquerque. The other user facility that has that is at Oak Ridge National Laboratory, and Karen Moore and David Cullen have that capability. They're highly oversubscribed because they're to-go prescribed site for all ERE users. So it's not that they don't exist. You just need to make the phone call or file once. I mean, you receive also from Oak Ridge and from Sint, you're receiving user facilities application. Just file those every 6 months.
Yeah, so
It's a one-pager.
Right. So the Oak Ridge folks actually use our liquid cell design.
I know. But those things exist. It's not like they don't exist, the user facilities.
Yeah, they don't. I guess because of the complications in the experiment. Certainly, I know the Oak Ridge guys are. Yeah, it's more of a collaboration than it is.
That is correct.
Yeah.
Yes, that is correct, because it's not a commodity, but you can write a proposal and you can collaborate. Not you, they can write a proposal and collaborate.
Yeah.
Okay, thanks again to.